There are two processes that are found in organic reactions and mechanisms, and they are bond breaking, sometimes called bond cleavage, and bond making or bond formation. They're equally important because you will see them occurring all the time in your reactions and mechanisms. So it's important to learn the basics. Once again, these are like the ABCs. We have to know them in order for us to read words, and the same thing has to be applied. So there's a very, very high emphasis on what arrows mean, what curved arrows mean. So let's begin with the first type of bond breaking. So if you have a bond that breaks by equally dividing, the word equally is very important, the electrons between two atoms in a bond, though this process is called homolysis or homolytic cleavage, bond cleavage. And it goes like this. So I'm going to use different arrows here. So watch how it looks. This bond is composed of two electrons. It's a pair of electrons. So I used these fish hook, they're called fish hook or single-headed arrows. And this is the transformation that actually occurred. Watch. This double bond was divided equally. So those two electrons were distributed equally. You should be able to see it now to A and B. So there's a name for these arrows. Let me make them more pronounced here. This is called a fish hook. Arrow. And they are for the movement of one electron. One electron. This is key. Notice this half-headed arrow should tell you that this is carrying a 1 electron, not 2. The double-headed arrow would be 2, so you might have guessed that right. There are just names for a few things here. These are called, they have a name for them, each. These are called free radicals. You heard about them before. In the process of aging, they play a huge role in biology and, of course, in mutations, etc. These are very reactive. Free radicals, or sometimes we just call them radicals, and very unstable because they want to find the closest thing to actually form a bond with to fill the octet. The second, so again, the one thing that you need to be aware of is that it generates an unreactive intermediate. So there is no charge, on uncharged reactive intermediates with unpaired electrons. So we call them free radicals. So again, these are uncharged. They have no charge on them because they have that number that they're supposed to have. So their formal charges would be 0. We'll look at examples. The second type is called, and this is more common and more important, is called heterolysis and or heterolytic cleavage. And what happens here is that you have an unequal dividing of the electrons, unequal division of the electrons between two atoms. So that's why it's called hetero versus homo. Hetero means not uniform or unequal. Homo means equal, kind of uniform, like what we did here. So you have right here this part, and watch how the arrow is different. So you know you have two electrons, you would draw this way. Okay, notice the double-headed arrow. And what you get is you get A and you get B. And now this is very critical. This is going to have a positive charge. This one has a lone pair, and it's going to be a negative charge. Think about it. This one took two electrons with it, deprived that one of, let's say, the octet, and therefore this would be positive and this would be negative. Of course, you can apply it in the other direction, so it would be like this. And once again, notice where the arrow is. Where the arrow goes, that's where your negative goes, because it's taking two electrons with it, taking two electrons with it. So this would be A plus B. And now again, you should be able to tell which one is positive, which one is negative. So the arrow went to the A. That means this is going to be negative. The arrow went away from B. So this should be positive. So it's very important that we write this. So you ask yourself, which direction will electrons go? That's the question, is how do we know which one, where does it go? Well, the answer to this is that when A and B have different electronegativities, the electrons go to the more electronegative atom. So we will see that in a second. Where do you, so mate ask, how do I know? Does it go to A or B? Well, you have to check the electronegativities. So if B in this case was more electronegative, that's why the electrons went to it. Again, it can, remember what we learned in acids and bases, it can accommodate the charge more readily. Here it went to A because A would be more electronegative. So there's no rule that it has to go from the left to the right or right to the left. Once again, be aware that where the electrons go, that's where the negative charge goes. Where the electrons go, that's where the negative charge goes. Where it goes away from, that's where the positive is at. So again, make sure you remember that. It did generate charge intermediates. Okay, so those have a name for them. Those are called charged intermediates. So you will see them in an example in a second. All right, so let's talk about heterolytic bond cleavage when Z is more electronegative. So when Z is more electronegative, let's say in this case, and this is really important that you remember, once again, if Z is more electronegative, it means that the arrow is going to go toward it, right there. And in this case, let's draw what would it leave behind. Okay, so the arrow went away from C, and it's a double-headed arrow, so it took this lone pair in there. So then, in this case, C has a positive charge. And Z now took the electrons with it. So that would be a negative charge. Okay, there are names for this, especially we're going to focus on, of course, the carbon right here. This is a cation, so we call it a carbocation. And it's an electron pore. You've seen this before in chapter 2. So electron pore means it's an electrophile. Loves electrons because it doesn't have the octet. Okay, now what if C now, C I meant, is more electronegative? So your arrow now would go toward C. Notice how I'm drawing it from the bond to C. It can't be anywhere. It can't go on the other bond. It can't go in the middle from that bond to the middle of the bond. Makes no sense. So it has to go, these electrons are going to C. That's what it means. Okay. So the arrow went to C, so it takes with it what? Yes, a lone pair. An electron. And of course, what's the charge on this? If that's where it went, that would be a negative. And of course, now Z would be the one that was deprived of those electrons, so it would be a positive. What's the name now of this? From general chemistry, anything with a negative charge, we called it a we called it an anion. So we call this a carbanion. Carbanion. That's an ion, and negative ion, that's an anion. So we put carb for carbon. It's electron rich. It's a negative charge and a pair of electrons. So obviously you should know the name of this. This is what we call a nucleophile. 95% of the chapters that will follow from here to organic also and organic 2 are going to be about electron rich to electron poor, electrophiles and nucleophiles. So make sure you have a good understanding of this. So now the next thing is go back to homolysis just to show you some examples. Here we go. So we have now homolysis means it's divided equally. So if it's divided equally, it means you split this pair of electrons between them equally, between them. And I'll put that here so you can see it. So in this case, again, those would be, this is called a carbon radical. And it is electron deficient because it doesn't have 8 valence electrons. Now, before we move on, these are in the middle, as we said, those are called, all of these right here. These are intermediates. In polar reactions, because polarity comes from the difference in electronegativities. So you have nucleophiles and electrophiles. So electrophiles and nucleophiles. So again, where nucleophiles react with electrophiles. Here in this one, these are in what we call free radical reactions. So these are intermediates in free radical reactions. There will be just one small chapter, and I will do only one in Organic 2 next semester. Just a few reactions. It's important, but it's very specialized. They're not as important and as useful as polar reactions. So absorb this, because when we come back in the next video, I will be able to apply. You should be able to apply now, let's say, heterolytic bond cleavage on this one and a homolytic bond cleavage on the next one. So radical reaction, and of course, this would be a polar reaction. Bromine is more electronegative, so think about it before you watch the next video. Attempt it on a piece of paper. It's okay to try it, and then you will check with me when I do it in the next video.